Imagine a technology that lets us peer inside the human body without a single incision, or find microscopic flaws in an airplane wing without taking it apart.
Yeah, we're talking about ultrasound. It's an incredible tool. It really helps us visualize the invisible.
But have you ever stopped to think what makes these devices so incredibly effective? What's actually going on inside them? Or maybe behind the bit that does the work?
Well, today we're doing exactly that. We're taking a deep dive into some really interesting new research. It's a scientific paper titled Nanoarchitectonics of Ethylene Propylene Diene Monomer, EPDM composites, reinforced with QL-Zen alloy for ultrasonic array transducers fabrication.
Okay, that's a mouthful.
It is, but it's fascinating stuff from Mirame White-Barakat and their colleagues. They're looking at a really crucial but often overlooked part, the backing material.
Right. So our mission today is to unpack how scientists are working on new materials, things that are low cost, high performance, and designed to make these ultrasonic array transducers even better. Faster, more durable, maybe.
Exactly. We'll get into the specific challenges these devices face and how this, well, pretty innovative combination of a common rubber and a special metal alloy might offer a surprising solution.
And this isn't just lab talk, is it? This is about advancements that could actually lead to clearer medical diagnoses for you, more efficient industrial checks, maybe even new ways to use ultrasound we haven't thought of yet.
Precisely.
Yeah.
It connects back to the real world in very tangible ways.
Okay, so let's dig into this a bit. We hear ultrasound all the time, but what exactly is an ultrasonic array transducer, and where do we typically see them? Is it just hospitals?
Right, so basically an ultrasonic transducer is the core component. It generates and receives sound waves, but at frequencies way too high for us to hear. That's the ultrasound part.
Okay.
It uses these tiny components called piezoelectric elements. Think of each one like a miniature speaker and microphone combined. It turns electricity into sound vibrations and then listens for the returning vibrations and turns them back into electrical signals.
Got it. So where does the array part come in?
An array just means you have, well, a whole bunch of these elements working together. They might be lined up, 1D or in a grid, 2D, sometimes even arranged in circles, what they call annular shapes.
Ah, so it's not just one blast of sound, but lots of them working together.
Exactly. It allows for much more sophisticated imaging, much more precise control over where the sound beam is focused.
That makes sense for getting a detailed picture. And the applications are pretty broad then, beyond the obvious medical scans.
Oh, absolutely.
Yeah.
While medical imaging is probably the most familiar thing, pregnancy scans, looking at internal organs, they're critical in industry too, for what's called non-destructive evaluation, or NDE.
NDE, like checking things without breaking them.
Precisely. Finding internal flaws in metals, maybe concrete, without damaging the structure. Imagine inspecting pipelines, bridges, crucial aircraft parts. These arrays mean better quality inspections, faster results, often giving you an instant image. It's huge for safety and efficiency.
Okay, so they're incredibly useful tools. But you mentioned challenges. Building these arrays isn't simple, is it? What are the main engineering hurdles?
Yeah, despite how useful they are, there are uh, two major engineering headaches. The first one, it's something called crosstalk.
Crosstalk, like interference.
Exactly. Remember all those tiny piezoelectric elements vibrating? If they aren't perfectly isolated from each other mechanically and electrically, their vibrations can sort of bleed over, interfere with their neighbors.
Ah, okay.
It creates noise, basically static in the signal, and that makes it harder to steer the beam accurately and degrades the image quality, like trying to hear one person in a noisy room.
Right, and you definitely don't want a noisy, unclear signal if you're looking for tiny flaws or making a medical diagnosis. What's the second hurdle?
The second big challenge is back echo reverberation. After an element sends out its pulse of sound, not all that energy goes forward. Some of it can actually bounce backward off the back of the element itself and then reflect forward again.
So an echo inside the device itself.
Pretty much. It creates more unwanted noise, obscuring the real echoes coming back from the target, whether that's tissue or a metal flaw.
Okay, so you've got this chatter between elements, the crosstalk, and then internal echoes bouncing around the reverberation. How do engineers actually stop that noise? How do you get a clean signal?
This is where our main topic comes in, the backing material. It's absolutely critical. It's a layer of material bonded directly to the back surface of those piezoelectric elements.
And its job is?
Its main job is to dampen, to absorb the vibrations of the elements very quickly after they've fired their sound pulse. Stop them from ringing like a bell for too long.
Okay, like a shock absorber for sound.
That's a great analogy. By dissipating that excess energy, it does a few key things. It increases the frequency bandwidth, basically, allows the transducer to work effectively over a wider range of sound frequencies, which gives you more information.
Right.
It also improves what's called axial resolution. That's the ability to distinguish between 2 points close together along the direction of the sound beam. So sharper images, more detail.
And it helps with that back echo problem too.
Definitely.
Yeah.
Especially for high-frequency transducers where precision is everything, that backing layer is essential for inhibiting those vibrations and preventing the back wall echoes from messing up the signal. So yeah, dampen waves, prevent reverberation, shorten echoes. That's its job description.
Okay, that makes sense. Now, for years, these backing materials have often been things like epoxy resins mixed with heavy fillers, right? Like tungsten powder.
That's been a common approach, yes. Polymer matrices, usually epoxy, loaded with inorganic fillers. Often heavy metallic particles like tungsten because they have the right acoustic properties, particularly high acoustic impedance and attenuation, to absorb that energy.
But there's always a push for something better or maybe cheaper or easier to make.
Absolutely. Those traditional materials, while effective, can be quite expensive or sometimes difficult and hazardous to process. So the search is always on for alternatives that perform just as well, maybe even better, but are lower cost, easier to handle, maybe more durable.
Which brings us back to this specific research. They're looking at a new combination. What are the stars of this deep dive again?
Right. The key players here are EPDM, that's ethylene propylene bimonomer, a type of synthetic rubber. You actually encounter it quite a lot, maybe in things like garden hoses, roofing membranes, car door seals.
Oh, okay. So fairly common stuff.
Relatively common, yes. And the other star is a specific metal alloy, QL-ZAN, copper aluminum zinc alloy.
Rubber and a copper alloy. That sounds unexpected, maybe.
It does seem like an unusual pairing at first glance, but the researchers explored exactly how putting this QL-ZAN alloy into the EPDM rubber would affect its properties as a backing material.
And they tweaked things, didn't they? They added something else.
Yes, a key variable was using, or not using, a coupling agent, specifically one called TMSPM3 trimethoxyethyl propylmethacrylate, another mouthful.
Yeah. What does the coupling agent do?
Think of it like a chemical bridge, or maybe glue. Its job is to help the metal alloy particles bond better with the rubber matrix, to improve how well they mix and disperse so you don't just get clumps of metal sitting in the rubber.
Okay, so it helps everything stick together properly. And they varied the amounts, too.
They did. They tested different concentrations of the alloy, ranging from 2.5 parts per 100 parts of rubber, they call that fur, all the way up to 20 or even 25 fur quart for some tests, both with and without that TMSPM coupling agent.
So quite a thorough investigation. They didn't just mix it up. They put these new composites through a whole battery of tests, right? Looking at sound performance, structure, stability.
Exactly. A really rigorous assessment. And this is where it starts to get really interesting when we look at the results.
Okay, let's start with the most crucial part for a backing material. How does it handle sound? How do these composites perform acoustically?
Well, they looked at 3 key ultrasonic properties. First, ultrasonic velocities, basically. How fast sound travels through the material. Both longitudinal waves, kind of straight-on pushes, and shear waves, more side to side.
And what did they find?
As they added more of the metal alloy, both types of sound velocity increased. Sound traveled faster. And interestingly, the composites where they used that treated alloy, the one with the coupling agent, showed even higher velocities.
Why is that good? Faster sound means?
It generally indicates a reduction in the space between molecules, a denser packing. This tighter structure is better at absorbing those unwanted back echoes we talked about.
Okay, so faster sound, better echo absorption. What was the next property?
Acoustic impedance, often labeled Z. This is a measure of how much resistance an ultrasonic beam encounters when it tries to enter a material. It's really important for matching between layers, like between the piezoelectric element and the backing.
You want a good match.
You ideally want the backing material's impedance to be similar to the piezoelectric material's impedance to allow energy to transfer efficiently into the backing to be absorbed, but also different enough to cause some reflection if needed for damping. It's a balance. What they found was that Z increased as they added more alloy.
And how did it compare to the standard stuff, the epoxy tungsten?
This was really promising. Several of the prepared EPDM composites, specifically ones labeled E0, E1, E2, E3, and particularly one called E6 from the untreated series, had impedance values ranging from about 3.08 to 3.5 mRails. E6 itself was right around 3.45 mRails.
And the standard is?
The commonly used epoxy with tungsten has an impedance around 3 mRails.
Wow. Okay, so these new materials, especially E6, were hitting that sweet spot. Very close match.
Exactly. It makes them excellent candidates just based on that property alone.
Okay, third acoustic property.
Ultrasonic attenuation coefficient, usually shown as alpha. This measures how much sound energy is lost or absorbed within the material itself as the wave travels through it. You want high attenuation in a backing material. You want it to soak up energy effectively.
So higher attenuation is better here.
Generally, yes, for absorbing unwanted energy. However, the study reported that the attenuation coefficient decreased with increasing Q alloy content. Now, this might seem counterintuitive at first.
Yeah, I thought you wanted it to absorb more.
You do, but how it attenuates matters. A lower attenuation coefficient here actually suggested fewer defects or gaps within the material's microstructure. It implies the material is more uniform. The energy absorption likely comes more from the inherent properties of the well-dispersed alloy within the rubber matrix itself, rather than scattering from imperfections.
Ah, I see. So a cleaner kind of absorption. How did the values compare?
Again, very encouragingly. Composite E6, the untreated one with 25 Fe alloy, had an attenuation of 3.07 dBc-meters, and E7, a treated version, was 2.96 dBc-meters,
And the epoxy tungsten standard?
around 3 dBc-meters.
So again, right on the mark. Acoustically, these materials seem really solid.
Very promising, yes. Across velocity, impedance, and attenuation, they showed characteristics very suitable for backing applications, closely mimicking the established standard, but with potentially simpler materials.
Okay, so they handle sound well.
Yeah.
The backing materials also need to be, tough enough for the job, right? They need to be stable. How did they hold up mechanically and when exposed to heat?
Good question. They looked at mechanical properties too. Things like Young's modulus, which tells you about stiffness, and microhardness, resistance to scratching or indentation. Generally, both stiffness and hardness increased as they added more alloy, which makes sense, you're adding metal to rubber. And this effect was even more pronounced in the composites treated with a coupling agent.
So the treatment helped make them mechanically stronger.
It seems so. They also looked at Poisson's ratio. This basically describes how much a material bulges out sideways when you squash it.
Right, like squeezing a rubber ball.
Exactly. And they found the Poisson's ratio decreased with more alloy, especially treated alloy. A lower Poisson's ratio generally indicates improved mechanical stability. The material holds its shape better under stress.
So the takeaway is they're strong enough to provide support, but maybe still flexible enough, being rubber-based.
That's the ideal balance you're looking for. Enough structural integrity, but compliant enough to allow the piezoelectric elements to vibrate properly and to conform well during bonding.
What about heat resistance? Transducers can get warm during operation, can't they?
They can. So thermal stability is important. They use a technique called thermogravimetric analysis, or TGA, which basically measures weight loss as you heat a material up.
Okay.
The results here were quite dramatic. Adding the Q alloy significantly boosted the EPDM's resistance to breaking down from heat, especially the treated alloy.
How much of a boost?
Well, for instance, composite E11, which had 20 U-core of treated Q alloy, showed a huge jump in thermal stability. The temperature at which it lost 50% of its weight, called T50, went from about 326 degrees C for the plain EPDM rubber all the way up to 476 degrees C.
Wow, that's a massive improvement.
It really is. It suggests that the well-dispersed treated alloy particles help restrict the thermal motion of the rubber chains, making the whole composite much more stable at higher temperatures, better durability in the long run.
Now, you mentioned the treated alloys showing better mechanical and thermal properties. Could they actually see the difference the treatment made, like under a microscope?
Yes, absolutely. They used a scanning electron microscope at SEM to look at the microstructure, and the images confirmed what the other tests suggest.
What did they show?
In the untreated samples, you could often see that the Q alloy particles weren't always evenly spread out. There were clumps, agglomerations.
Not ideal for consistent performance.
Exactly. But in the samples treated with that TM-SPM coupling agent, like composite E9, for example, the alloy particles were generally smaller and much more uniformly dispersed throughout the EPDM rubber. Far fewer clumps.
So the coupling agent really did its job, creating a better mix.
It seems so. And that improved structure, that better morphology, is likely the direct reason for the enhanced thermal and mechanical properties we saw in the treated samples.
Makes sense. Did they look at density too? Does it matter?
They did. Density is relevant because you want a material dense enough to effectively dampen vibrations,
Okay.
but not so heavy that it overly restricts the piezoelectric element or makes the transducer cumbersome. And the densities increased with more alloy, as you'd expect, but stayed within a reasonable range. The maximum was about 1.058 kg meter, suitable for the application.
Okay, so the lab tests look great, promising acoustic properties, good mechanical and thermal stability, especially with the treatment. But the real proof is in the pudding, right? Did they actually build transducers with these?
They did. That's the crucial next step. The researchers fabricated 10 different linear ultrasonic phased array transducers, real working devices.
10 of them, using different versions of their composites.
Yes, each one incorporated a different QLZN EPDM composite as the backing material. They used various concentrations, both the untreated and the treated alloys, a proper head-to-head comparison in a real-world setup.
Fantastic. And what was the key measurement they used to see how well these finished transducers worked?
The main performance metric they focused on was the signal-to-noise ratio, or SN.
Signal to noise. We hear that term a lot. What does it mean specifically here, and why is a low value what you want?
Right, it seems a bit backward, but SN measures the strength of the desired signal, the useful echoes you want to see relative to the level of background noise, like that crosstalk and reverberation we discussed. So a high SN means the signal is strong compared to the noise, which is usually good. But in this context, when evaluating the backing material's effectiveness at reducing noise, a lower SN value actually indicates that the overall noise level in the final transducer signal is less.
Ah, I get it. Less noise overall means the backing is doing a better job damping those unwanted echoes. So lower SN equals clearer signal.
Precisely. For medical imaging or finding tiny flaws, minimizing that noise floor for the clearest possible signal is absolutely paramount.
So drumroll, what did they find? Which composite produced the transducer with the lowest SN, the clearest signal?
The results were really compelling. All the composites did a decent job reducing noise compared to, say, having no backing, but one stood out.
Which one?
The transducer built using composite E6. That's the one containing 25 sphere of the untreated QLZN alloy.
Wait, the untreated one?
Yes, that specific transducer recorded the lowest signal-to-noise value, just 0.018.
Wow. So despite the treated composites showing better mechanical and thermal properties in the lab tests,
When it came to the ultimate goal, producing the cleanest signal in a functioning transducer, the E6 composite with the untreated alloy was the champion. It demonstrated exceptional effectiveness in dampening those noise echoes.
that's fascinating. And you mentioned earlier that E6 also had acoustic impedance and attenuation very close to the standard epoxy tungsten.
Exactly. Its acoustic impedance was around 3.45 mRails, attenuation around 3.07 dBcmers, both very close to the 3 mRails and 3 dBcm standard. Its mechanical properties were also deemed suitable.
So this raises a really interesting point. The best material on paper, in terms of thermal stability or perfect dispersion via treatment, wasn't necessarily the best for the final application's key metric signal clarity.
It's a fantastic example of how lab results on material properties don't always perfectly predict performance in a complex system. The interaction between the backing and the piezoelectric elements, the overall device acoustics, it's complicated. And in this case, the untreated E6 composite just hit the sweet spot for noise reduction in the final device.
And crucially, this E6 composite has some big practical advantages, doesn't it?
Huge advantages. It's potentially relatively low cost using common EPDM rubber and an alloy, without the extra step in cost of the coupling agent treatment. It's likely easier to prepare for the same reason. And being rubber-based, it boasts good abrasion and tear resistance, suggesting a potentially longer lifespan compared to more brittle epoxy-based materials.
So cheaper to make, easier to make, potentially lasts longer, and gives the best signal clarity. That sounds like a genuine breakthrough.
It really does check a lot of boxes. It highlights that sometimes the simpler, more cost-effective approach can yield superior functional results for a specific demanding application.
Okay, so let's recap. Today, we've taken a real deep dive into the often hidden world of ultrasonic array transducers, focusing on that critical backing material.
And we've seen how these new composites, blending EPDM rubber and a copper aluminum zinc alloy, are showing immense promise. Specifically, how that E6 composite, even without treatment, could revolutionize performance.
Yeah, improving everything from the clarity of the sound signal, that crucial signal-to-noise ratio, to the potential durability and, importantly, the cost-effectiveness of these devices.
And remember, this isn't just tweaking a component in a lab. This is a potential leap forward for technology that affects us all. It could mean clearer, more reliable, maybe more accessible medical diagnoses.
And more thorough, faster, safer industrial inspections for everything from pipelines to airplanes.
Exactly. It's a brilliant example of how material science, often working behind the scenes, is constantly pushing the boundaries, improving the technology we rely on every single day, making the invisible just that little bit more visible.
It really underscores how innovation isn't always about the completely new gadget, but sometimes about perfecting the crucial, maybe overlooked components inside, like this backing material, the silent hero, you could say.
Well put. Sometimes the unsung components are what make the whole system truly perform.
So, thinking ahead, imagine the next wave of medical tech. Maybe handheld, truly portable diagnostic devices that doctors could use anywhere thanks to more robust and affordable components like these, or maybe inspection drones for infrastructure getting even better.
The possibilities open up.
It really makes you wonder, doesn't it? What other hidden components inside the technology we use every day are just waiting for their own deep dive makeover? What unsung material might be the key to the next big leap?